Today we are going to talk about queuing theory. In fact, it's perhaps an oversimplified view to get you familiar to some degree with one special type of queue, the MM1 queuing models. But I'd like to start with this chart to give you a more intuitive feeling. We've been talking about different routing algorithm, okay? But you see that under no load, this is sort of the intrinsic latency, if you wish. How long does it take for you to get from one location to, on average, to another? As the traffic increases, that reality didn't change, and especially under deterministic routing, such as dimension order routing, it still takes that long to get there. In terms of going through the routers. So why does it take much longer when we have more traffic? Several times longer. And that's clearly because of queuing. You're waiting for others to use the resources. So how do we try to wonder? We can obviously do this simulation, and we see queuing effects directly. But we can also try to understand it a little bit more mathematically, and that's what we're going to do. And that we usually need to know what type of traffic pattern or arrival models of request at a particular node is. And the most commonly used one is sometimes called the boson arrival model. It's really this property over here, independent arrival model, that says if you chop time into these small segments, then in a particular segment, the probability of one arrival is lambda delta t, proportional to the size of the time segment with a constant of lambda. And you can ignore the probability of more than one arrival because that's O delta t. So why do we use this model? And we will see that it has, why is it called Poisson? I'll show you in just a moment. Why is it an independent model? Sometimes people call this the exponential model. So let's perhaps derive the math just a little bit, okay? Okay, so I'll set this down so I can write. First, we want to know, let's say this is my arrival model that for the next nanosecond I look at it, or some small delta t, I look at it, I know the probability of one arrival is blah. But let me ask the question of t. And in particular, maybe the expectation of the t. How long do I need to wait before I see my first incoming packet? And so that, let's say you get that packet t at time t, or that's your first customer. It doesn't matter. Any queuing models, any application of the queue would work. We actually know this is elemental probability. Okay, we already told you all these independent models, right? They're independent. That means if my first customer arrive at time t, that implies I got nobody coming in this little time segment, none in that, and so on. Okay? And we know we know the probability of each event, right? Because that's simply 1 minus lambda delta t. Nobody arrived. Nobody arrived for this many time segments, and only one arrived in that little time segment. So this is the probability of t falls into this tiny segment of t minus delta t. Let's start that with open region NT. Okay. complicated. What is all of that? Well, this thing should remind you of something that you might have seen, which is this form, especially when n goes to infinity. In the past experience, I asked this question. Most people don't know what it is or forgot. I would suggest you take your calculator, just punch some number in, try some n. Your scientific calculator should do you justice, and see if you recognize that number. I'll give you a hint. You can pause the video and try this if you wish. But the hint is this number is something like that, very close if you use a large enough n. So you probably recognize that number. Yes, that's E. So that can be translated a little bit, or actually just the first part of it, not that part, just this part can be translated a little bit. Okay, that's just, sorry, why did it use a different color? For consistency. Yeah, palm rejection problem. This would be 1 minus delta t raised to the lambda delta t minus 1. That would be something. So n, 1 over n and n format. But no, we have to complete the top because that's not what it used to say. Now this is cool. And of course we drag down the. Now this is cool because this is simply that format, and all of this we're talking about is indeed as t goes to 0, delta t goes to 0, and therefore this is simply e to the minus delta t. And we can put the lambda over here and the delta t over there. So why? Because, remember, what is this? The probability density function's definition is ft is limit as delta t goes to 0, the probability, I'm not going to write the whole thing, over delta t. Therefore, we can simply carry this down, and this is quite straightforward. Did I do anything wrong? Well, one way to check is, let's see, this is probably the density function, okay? Which means if I integrate it over the entire allowed range, 0 to infinity, cannot be negative, this value should be 1. So question is this 1? Well, let's find out. Look at this. This is really convenient, isn't it? That's part of the beauty of this type of arrival model. The math just works for you. That is simply the derivative of minus e minus lambda t. That's that derivative. So if I want to calculate this thing over here, let's move that. If I want to calculate that, I simply need to do, what did I do? I simply need to do this. That's the indefinite integration, and calculate the range. And this, give me a little bit more space to write. Okay, what is this value? When t is infinity, it's 0 because it's minus. There's a minus sign over there. It's 0. When t is 0, well, it's minus 1. Minus 1. Indeed, it is 1, so check. Okay, this is a proper probability density function. Is it the right function? Yes, it is, because I checked. But that's pretty. Okay, let's go back to the expectation. You know how to calculate expectation? Slightly more complicated. Density function times t, so this is e of t, again in the entire range. Okay, this is not good. Well, let's look at this a little bit. If you recognize this type of integration, you might remember this thing called integration by parts. If you don't, and last time I was taught about that or being tested on that was when I was in my freshman year. That's a long time back. Okay, but here's my mnemonic, right? I know this. It's hard to forget that, right? So I want to integrate on both sides. It should be true. Let's just do indefinite integration, right? But the left hand side, I don't have to do that. I don't have to put an integration sign. It's just uv. So that's it. If you have a form that's in this in a multiplicative format, you try to map it such that it translates into something else. Hopefully that something else is simpler. And obviously you want v to be t because you're translating that to t prime. So v prime is 1. Nice. So what's u? U is whatever remains, which is the ft. Okay? But that's the u prime. You want u prime to be in that form. Okay, so what is u? U has to be minus e to the minus lambda t. Therefore, u prime would be, the minus cancels out, lambda e, minus lambda t, no? So armed with these substitutions, we would say that this integration over here is uv minus that. All right? uv. U is this over here. V is simply t, so that's just minus t e minus lambda t. This is definite integration, so we need to know where it is. Maybe I'll move this somewhere else again. Let's have a bit more space. Okay, minus, right? Looking at this over here, it needs to be a minus the integration of uv. U would be this thing over here. V prime is 1, so I don't even have to do that. I forgot dt over here. Wait a minute. I've seen this. Of course, first I cancel out that. Maybe cancel out. I've seen that. Have you? I've seen that. Where was it? It was here. We integrated this. But ft has a lambda in it. This doesn't have a lambda in it. And ft integrated a whole thing is 1. This doesn't have the lambda, so it's just lambda times smaller. Ooh. It's just lambda times smaller. So that's good. This whole thing equal 1 over lambda. What about this part over there? You're in luck again. When it was 0, obviously, thanks to t being 0, this whole thing is just 0. When it's infinity, it's a little harder. One is infinity, minus infinity on the top, that's a 0. The other is an infinity. 0 times infinity. It's unknown. It's not a fixed thing. Well, but e is a much faster function. You can try this yourself. So this whole thing would be 0. So it doesn't matter. At both extremes, they're all 0. This is just a 0 term. So that whole equation is simply 1 over lambda. I forgot an equal sign there. Okay. That answers our first question. And it was kind of what you intuitively would have guessed. If my arrival rate is somehow lambda, what is my average time? It's 1 over lambda. So that's good. Thing one, it's good. This number is clean. We like it. Why? What else do we like it about? And let's see. Let me explain why it's called a Poisson process. So now let's think about why it's called Poisson model. I'll tell you a story, but maybe first to flash this a little bit, what we just derived is the probability density function is in the form of that. The expectation of time, this is the arrival time. When you are standing at a place looking or counting your customer, when is the expectation, when is the expected time your next customer will arrive? At that point, it's 1 over lambda. And you will hear about Poisson distribution, and it's a complicated one, and we'll derive that. So the story is this. Okay, and this is totally different thing. This is Poisson distribution. Why is that? Poisson was, I believe, a surgeon. Okay, don't quote me on this. I heard this story. I thought it was funny. You should know, but I cannot vouch for its veracity. I'm not a historian. So in the World War I, people fight. There's armies. I believe it was millions of people. The Prussia front put forward millions on the other side. They fight. It wasn't a modern warfare with huge bombs. It was anyway, no Panzer division from Hitler. So guess what they use a lot to transport stuff? Donkeys or mules, whatever. And guess what they like to do? Kick. And guess what's the consequence of that? People die of donkey kick. And Poisson was a surgeon, was sent from the French side to fix the problem, to get a solution or whatever, or just to cure the ailing soldiers who got kicked, I guess. So he did a study. He said, let's see how this goes. And as a good mathematician, he starts to create models. And that's what he got. So in a amount of time, in a fixed amount of time, this is the same arrival model. He assumed a donkey wants to kick someone, or kick, or just kick, at a fixed probability. In any little time period, the probability of donkey kick is the same, and it doesn't change. The next cycle is the same. It doesn't depend on whether the previous one already had a kick event or not. And what he wanted to find out, this is a slightly different perspective from the time. This wasn't, I'm standing here, how long do I have to wait for someone to be kicked by a donkey? But rather, in a fixed amount of time, how many kicks would I get? Okay, if your answer is, oh, I think, this is the arrival time, you get this many on average, then you're right in the expectation sense. You know the average, meaning I have the chance of being kicked. I've 40% chance of having one kick, 40% having two kicks, and so on and so forth. The expectation is this value. He actually wanted to know more. He wanted to know how many kicks, what is the probability of any number of events. This is the same discrete probability problem that we were just encountering. Okay, let's chop this into a lot of little things. Each one will be a binary event. It either has a kick or not. Cannot have two, remember? And so I have t over delta t sections. Let's call that n. I have n little time domain or time periods. How many kicks would I have? What's the chance I have one kick? This binomial distribution. It's fairly straightforward. If I have one kick, that means out of all n, I have to pick one, and it will have, so this is n choose one, let's just call that n, and it has the probability of a kick, okay, and the probability of not having a kick raised to n minus 1 power. Yes? But this is, so this is probability of, let's call that P1 equals that, right? And what happened? Okay. Okay, I don't know what happened. Let me just write over it. Limit delta t, let's ignore that, goes to 0. This is P1, yes? Okay, but how do we generalize this? Let's say I have K events. It's K kicks. Actually, 1 second, let me use the same. Yes, it's K. Use the same variable, then it's limit delta t goes to 0 and choose K delta lambda t raised to the k's power 1 minus delta lambda t lambda delta t and minus k. Okay, got that. Move this around, say there. Okay, what is this value? Not very sure. Well, let's try to derive this just a little bit. What is n choose k? N choose k is this, and n over 1 to n minus k plus 1 over k factorial. Yes? Okay. But as delta t goes to 0, n is infinitely larger than k. So minus 1 minus all these finite number really doesn't matter, right? So this is the same as k factorial n raised to the k's power. No, that's what we know. I actually had an error here. This is n minus k that I forgot. Okay, so now we know this part, which is here, and we want to plug that in, so let's just continue. Okay, right here. This becomes n raised to the k's power delta t also raised to the k's power over k this, and then 1 minus delta t raised to the n's power. Again, I'm using the same idea. N is infinity, k is a small constant. Doesn't really matter whether I minus k or not. What is this? Remember? We've seen this before. N is merely t over delta t. Okay. So if we want lambda over here, then we would get a minus delta lambda t on the top to make this e, so that's what you're going to get. This whole thing is therefore e raised to the minus lambda delta t, and this whole thing n delta t multiplied together is just capital T. So that's lambda capital T raised to the k's power over k factorial. Now we don't need the lambda, the limit. So this is p k event, okay? So in the probability that we describe, we're not going to use the t or things like that. We're just going to say, suppose we have k event when we expect lambda events, okay? Or you can call it the lambda t events. Lambda is the rate. We used to use lambda for the rate. Now we're swapping out this lambda is the expected value of it. Maybe we should use capital lambda, whatever I'll use. In my slides, I'm using lowercase lambda, but let's, for the sake of clarity over here, then this would be lambda k over k squared e minus lambda. That is called the Poisson distribution. Okay, now you know where the name is coming from. So here, okay, why is this flipping out? Give me a second. Let's reopen this. Okay. I really closed it during our recording. Sorry about that. Technical glitch. It's not supposed to do that. Okay, now that's the distribution. Here, our lambda is the big lambda, if you wish. It's right over here. And that's called the Poisson distribution. So what this really says is this: if I have, let's say, a period of time where I expect one event, and I go in and observe. Well, you know, the bus comes once every hour. I stay there for an hour. What am I expecting? If I stay there for infinitely many 1 hour period, my average would be 1 per observation. But if I want to understand the distribution of these 1 hour observation window, about 36-7%, I would expect to see nothing. Another 36% I would expect to see 1, and so on. So it's more spread out than you see the expected value in every window. Okay, so the larger the lambda, the more spread out it is. For instance, in lambda equal 10, 10 is perhaps the most likely outcome. I'm not sure, I need to calculate. It may be 9, but 9 is just as likely, if not slightly more so, and so on and so forth, for all these other 8, 11, 7, 12, and so on. So that's what you expect to see. And this distribution is the Poisson distribution. Okay? Okay. Now, that's where the name comes from. Now let's get back to the expectation of time. Here we want another property to be understood. And this property is the conditional property. And what we want to say is this. Okay. This time we want not the probability density, but just the cumulative probability. So we want to know, let's call that T1. This conditional, I'm sorry, let's write this carefully, legibly. We want to know this. What does that mean? That means I want to know, I have already waited for half an hour in my bus stop. How much, what's the probability it will arrive, the probability distribution that it will arrive in T1 time? Okay, I've already waited this long. How much longer do I have to wait? Before you say, okay, that's easy, your expected time to wait is what we can derive the probability time fashion, and then we can run the expectation value. So to put it in understandable terms, in an analogy, the bus is supposed to come in an hour, every hour. I've waited for 30 minutes. Knowing that, how much longer I need to wait? If your answer is 30 minutes, you're not alone, but it's incorrect. I'll give you a slightly different analogy or a scenario. You might understand it a little bit better. And this is the insurance industry or whatever, the life insurance industry knows this inside out, right? Let's say US population life expectancy is, I don't know, 80 years, doesn't matter what the number is, okay? And you've already lived 79 years. How much longer do you expect to live? Now you know it's highly unlikely for you to say, oh, 1 year, you're gonna die after your next birthday. If you really answer that, let me ask you, the expectancy is 80 years, you've lived 82 years now, how much longer do you expect to live? It would be silly if your answer is -2 years, okay? But to perhaps show you more visually, let's imagine this is my probability density function of people's own life length, age, and this is probability, and it goes something like that. So your life expectancy in this picture may be somewhere here, okay? That means as a group, people live this long. But suppose you're already in here. That's my condition, that you've already lived this long. Then your expectancy would be somewhere here for this group over here, and your expected remaining life would be this much, not negative, which doesn't make sense. Okay, so to show you how this relates to our problem now is this: we've already waited for t0. What's my probability of waiting less than t1? Okay, and for that, let's draw the probability density function and also the the cumulative distribution function for our Poisson arrival model, the independent model. We already calculated this here that I highlighted. Okay, so it's lambda for the it's lambda e for the for the density function, and this plus some constant for the cumulative distribution. Because this at t is -1, at t equals 0 is -1, at t equals infinity it's 0, so the offset is wrong. The real function is, this is your PDF. It's probably something like that, and your CDF, which tells you the cumulative area, goes like that. This is your CDF. And let's draw T1 over here and T0 over here. So what are we talking about? T less than T1 would be, let me mark that as yellow. Okay, we care about this whole area. Oops, a little overdrawn. Let's see if I can clean that up. Okay, that area. What is the value? Now that we have the CDF, it's very easy. It's this value over here, the X value. Okay, so but the condition probability is t is already greater than t0, which means it's not just the yellow area, but it has to be the subset of it, which I color red over here. But it's not the probability shown in here, it's the conditional probability, which means it has to be relative to everything that is greater than, including the green area underneath that. Okay, so this is how it's supposed to be. P, remember, P A under condition B is really P A and B both happening over PB. Yep. So the top would be T less than T1 greater than T0 over P T greater than T0. Okay. So we just be a little bit visual here. What is the color that satisfies the numerator? It's less than T1 over here, and it's greater than T0 over there. So it's red. What is greater than T0? It's red plus green. Yeah, that's what we're calculating. So let's go on with it. Okay, what is the top? The top is easy. We know yellow. We know yellow plus the only part that the yellow, I mean this one. I mean here. Okay, exclusively yellow part. This part. The yellow part is the only part that t is not less than 0. Okay. By the way, this is lambda. Oh, lambda e minus lambda t. Here, this is e minus lambda t plus 1. Okay, that's the cumulative function. This is the density function. So, what is the yellow part's value? It's 1 minus this value, okay, which is e. So the bottom is just 1 minus e plus lambda t plus 1 t0. Okay, let me do this better. It's 1 minus, because we're not interested in the yellow, it's t greater than anything that is non-yellow, or red plus green, right? That is the bottom. Anything smaller than yellow, that's easy. That's just e minus lambda t0 plus 1. This is its value. So 1 minus that is the bottom. What's the top? The top is this value minus this value, which is 1, no, I have an arrow over here. There is a, okay. Let me erase that box. This has to be minus. Let me make sure. Yes, there is a minus sign. I wasn't confused. There is a minus sign. I was wrong in writing this down. So okay, there is a minus sign inside. That's why it doesn't feel right. And the top is, if it's less than T1, that is 1 minus e minus lambda T1 okay? But it has to subtract the part that is yellow. So this value is here, which is the area underneath the red and yellow. We have to subtract the yellow, which is 1 minus e minus lambda t0. Okay, let's clean this up. The two negative sign cancels, 1 minus 1 goes away, so really the bottom is just this. The two ones cancel out, and we make, let's rewrite this, e minus lambda t0 minus e minus lambda t1 over e minus lambda t0. Okay. Multiply by e lambda t0 both upstairs and downstairs. We get 1 minus e minus lambda t1 times e lambda t0, right? Which is really just t1 minus t0 in parentheses. This is the probability. What does this mean? What does this number mean? This happens to be the same as p t less than t1 minus t0. And let's try to understand what this means, perhaps going to the bus analogy. Now let's say I have a bus that arrives at an average rate of 1 per hour. Okay, and I've already waited for t0 is 2 hours. Okay. Now, that's a long time. I expect T1. I expect to wait T1, let's say it's 3 hours. Okay, what is the probability I wait for 3 hours? Normally, the probability of waiting for 3 hours on a bus that arrives at 1 hour, you can look at this, right? It's e minus 3. Okay, that's 95%. 95% of the chance I would get this within 3 hours. I've already waited for 2 hours. What's my chance of waiting no more than 3 hours? It's no longer 95%. It's the same as the difference of 1 hour. And you can know what 1 hour is, 1 over e, 75%. It's much more reduced. So basically, the thing is this curve's shape is exactly the same as you start to carve them. Okay, this portion that you carve, I'm already interested in this smaller world that my wait time is greater than t0. In this shape, in this region, the shape is exactly the same as the same curve of starting from 0. Okay, this is an exact replica. So waiting 1 hour is this chance, waiting 3 hours is that chance. So it takes, you've waited for 2 hours, too bad. Your odds of getting a bus has nothing to do with the fact that you've waited for 2 hours. In some probability distribution, that's not true. In the exponential density function, it is true. Okay, this comes directly from the fundamental assumption that it's an independent arrival model. You've waited for this cycle, it's passed. Too bad. The next cycle is another rolling of dice. So you've waited for 2 hours, you've flipped a lot of dices, there are lots of little delta t regions for the bus to come. The bus didn't come, unfortunately, and there is not a lot that you can do. And this is the memorylessness property. Okay, I don't know why it's keep on ejecting it from memory. This is the memorylessness problem. It doesn't remember. Sometimes called the Markovian property. Okay, I don't remember what happens, and therefore the past history doesn't really matter. Fine, we have this property. You need to remember that it's really coming directly out of the independence assumption in the model. It's not very surprising. And next, we want to derive what happens if I have a Markovian arrival model as well as a Markovian departure model when I'm serving something. I want to know how long the queue is.